load faster too if they're shorter. I wonder if that'll be like a.
Yeah, probably.
I wonder if it cares if they're discrete packets versus one large. Who knows network stuff?
I don't know, but I would assume that works.
I don't know. I would assume two.
Or you put something bigger on a computer, it's going to take longer to.
But the sum total is still the same. Like, does that matter? I don't know. I'm thinking out loud here. Anybody know the answer? We'll Google it later.
Which will be longer.
Well, I mean, if I've got one 18 gig video versus 18 1 gig videos, does the network care? Is that different bandwidth from a bandwidth point of view?
I bet it is. I bet it's quicker.
That's agree with me.
When it has less information, the
When you try
process
to
is
upload
much
like
quicker.
50 pictures all at one time, it takes a lot longer than if you upload like individually.
Right, but the question I had, and I don't know the answer to this, when I upload 18 videos to YouTube, is it trying to upload all 18 at once, or is it does the first gig, then the second? Well, then what's the difference between that and just putting one 18 gig video up? Because it's just pulling 1 gig, then 2, then 3. I don't know. I'm just putting that out there.
It's maybe in a
You see
big.
results faster, you see them loading individually.
Well, yes, you would see the, right, but the overall, having all 18 up, correct, you would see the first gig, then the second gig, yes. That's kind of like that.
All in
Right.
one is trying to do it all at once.
You see results and it makes you happier.
You see results and it makes you happier. There we go. Baby steps. I'm glad YouTube heard all of that. That's great. All right, let's get into the first of our two parameters. Here's the first topic I'm going to play with today. We're going to estimate a population proportion, which we call little p. Little p, that holds little p, using a sample proportion, which we call little p hat. There is an overriding goal. There is an overriding goal. Because we're going to estimate two parameters in this class. The population proportion and the population, do you remember? The population proportion and the population mean. Exactly, well, you got to be brave, my friend. The population proportion and the population average. And the overriding goal of both of those is the same. Okay? The overriding method, I was going to say goal, method, is the same. Whether you're talking about a population proportion or a population average. So this 3 steps I'm just about to give you right now is going to hold true not just for today's proportion, but also for Tuesday and Thursday's means. The first thing you're going to do is you're going to gather, that's one word, gather a simple, random sample. And I'm going to put the word ish over here. What does it mean for a sample to be random? What does it mean for a sample to be random? Do you remember, when you hear the word random, what do you remember from your previous statistical studies? Any words that pop to mind? Any words that pop to mind? Say that again, Chris.
The sample is big trend.
What does that mean? Good, I love that. What does that mean, though? What does that mean? I'm going to pick a random student from this class. You ready? Chris. Now you laugh. Couldn't I have picked him randomly? I'm going to pick a second random student from this class. Lindsay. You laugh again. Isn't that random? Couldn't that be random? How would you be convinced that I did it randomly? Third random student, Eric. You're all laughing. Maybe not at that time. But I could have drawn those 3 randomly, correct? What would I have had to do to convince you that I drew them randomly?
Random is putting everything into one bowl and picking out something where you can't see.
Which means I could have gotten these 3 guys that way, couldn't I? Especially without replacing them.
Yes.
Good, but it's not likely, is it? It's not likely. So there's about 30 of you in this class. The chance of me grabbing Chris first is 1 in 30. That's pretty unlikely. That's just about the same as pulling 5 black cards out of the deck, isn't it?
Yeah.
So, and you were suspect then too. Good for you. Then I make it worse by grabbing Lindsay and then Eric. So it's 1 in 30, 1 in 29, 1 in 28. It's getting less likely by the pool, correct? Cassie just hit on the definition of random. Every possible sample has what? blah, blah, blah of being chosen.
Because of chance.
Good. I was going to say the same chance, equal chance of being chosen as any other sample. That's why I can't say, I want to randomly survey community college students. Hey, what are you guys doing right now? Can't do that. Because there's no chance of any other school, let alone another class at COCC, being chosen. So in order to do a random sample, generally you have to use some kind of a randomizer, whether it's random digit dialing from Gallup, whether it's putting them in a bowl and pulling cards out. That's the best way. William Gossett, we're going to talk about him next class, I think. The guy that invented the t-distribution, which is the hugest part of studying means. He actually did that with papers back in 1899. He did it with paper to do simulations to get random samples. So it's old school, but it works. It's essentially the same thing as using your TI to hit rand int over and over again. It's even better because it's truly random. I saw a hand. Chris, was it you?
You asked me
Oh,
the random number generator in Gallup.
It's not, it's right, it's ish. It's ish. That's why I put random ish.
Yeah.
Anytime you use a computer to generate random numbers, it's not.
Right.
By definition of random, it can't be algorithmic.
Yeah.
But that's all a computer is algorithmic, isn't it? So it's using an algorithm to generate random numbers
That aren't so random.
that are computerized algorithmic. So it's a bit of a chicken egg kind of thing, but they've gotten really good. And for our purposes in this class, they're fantastic. I love Excel. I love the TI's randomizers. They're good enough for what we need to do. And you guys, if you need better ones when you go into your careers, you'll have them. You'll have them at your disposal. And there's always the bowl with papers inside. Although that did backfire with the Vietnam draft. I feel silly bringing that up anymore because it's been so long ago now. But when they actually created the draft, the first of 4 years of draft in Vietnam, they put capsules with birthdays in a big
Right.
lottery tumbler
Yeah.
and pulled birthdays. And
Like
if
a
you were
bingo-
pulled
like a
early,
bingo.
you were almost guaranteed with the hand crank.
Yeah.
And they had like the head of the House of Representatives pulling the balls out, reading the numbers off. If you were pulled first, you were almost guaranteed to go to war. And if you were pulled last, you're almost not guaranteed. And the distribution of the birthdays is highly skewed, which you would not expect. You would expect the same numbers from the first to second to third to fourth quarter. If you were born, I think it was October through December, a higher percentage of those guys went to war than January through March.
Why?
Nobody knows. I don't know if it was just the process itself was flawed, but that first year's draft, it was a goofy, some people say that they were trying so hard to make it random that they failed. I mean, I don't think anybody really knows why. It could have just been, it could have been a fluke too. It could have just been one of those data points that was so far away, even though it was fine, we just got a bad sample.
Or what if a lot of people have birthdays in between?
But you remember from 243, birthdays are roughly uniformly distributed. Remember we actually tested that in 243. I asked you guys when your birthdays were. We had matches and we had clumps, but they were spread out throughout the year. So good questions, which there's no good answers for. And nobody would even care, except it was Vietnam. It's one thing if you're selecting $100 to give to somebody randomly on the street. You're talking about somebody's life.
Yeah.
So it was a huge deal. It was a humongous deal. So anyway,
Poor kid.
you got your simple randomish sample. The next thing you do is you find the center of that sample. For us, it's going to be p hat. For us, it's going to be p hat. Next week, it'll be x bar. And we're going to keep p hat and x bar going all term long. Those are the only two I want to play with all term long. Because if we can use these two over and over and over again and get the overriding idea of inferential stat on those two, anytime you guys have to do any other statistic out in the world, you can apply what you've learned in here to those. That's kind of my point of cutting s squared out and sigma squared out. If you can deal with these guys, you can deal with anybody. You can deal with the median, you can deal with the mode, you can deal with my CPR class I mentioned to you guys, that goofy final exam in CPR. I had to invent a test and its own test statistic for that. But by the end of the course, when we analyze that, they're going to be like, this makes perfect sense. If I do it right now, you'll vomit and throw something at me, shoes, with vomit at me. But by the end of the class, you'll be like, oh, duh, you just get the center and you spread, and then you're done, you're done. And that's exactly what you do, because that's number 3. You apply a margin of error. And these things, depending on what you're reading, which textbook, which poll, which research entity, sometimes they're called MOEs, sometimes they're MEs. I think your book calls it an error bound or an error range. Look for the word error. An error, I know, has kind of a negative connotation. It's not. Your measurement in number 2 has error in it. By the simple fact, remember all those little blue diamonds? How they were all over the place? There's error in your sample. The only way to have no error is to go get the entire population. Impossible. So there's going to be error in your sample. So the margin of error controls for that. It controls for that. So what you're going to do is you're going to take that p hat and you're going to add and subtract the error to that, or the margin of error. Or you're going to have the x bar and you're going to add and subtract the margin of error. And what I want to do over the course of the remainder of today is get you kind of used to the margin of error on this guy. Because it isn't the same margin of error on the proportion as it is on the mean. One's a percentage. A proportion is a percentage. 0.75, 75%. Chickens. What's the probability? You go to the store and you buy a baby chick. What's the probability the baby chick is actually female?
9.9?
Point.
9.9.
No.
0.9. 90%, Cassie Moore, we know that. 0.9. 90% of those little tiny pullets that you buy are actually female. 0.9, 90%.
I'd like to know how you retain that.
How I retain what?
Uh,
Okay. Because we talk about chickens a lot at Chick 43. What's the average weight of a pullet? I have no idea. But it's a measurement. It's not a percentage, right? You can say this year's flock is 10% lighter than last year's flock. But the number itself is actually a measurement. So these are going to be percentages, which means the margin of error has to be a percentage. This is going to be some kind of a measurement, which means that has to be a congruent measurement. Pounds, pounds, inches, inches, miles, miles, whatever it is. This is always percentage, percentage. Always for a, so a proportion, you can also use the word percent or probability. I mean, they all kind of mean the same thing. Proportion, percentage, probability, they all mean the exact same thing. So here's a question I have for all of us. Roll some pennies today. We're going to collect some data right now.
You do that.
I know you need a new bag, yeah. I thought I got a new one, but I think I lost a new one.
I think there's literally a whole bottom.
Is there, oh, look at that, you are correct.
There's two.
There's 2 holes. We're getting new bags this weekend. I can't even open the damn thing. All right, here's a penny. Old school pennies. Old school pennies. We'll trade your bag, almonds for pennies. So, if I flip this penny, assuming that it's a fair coin, and I think these are, as far as I can tell, and I put it on my hand, what's the chance I did heads? Good, and that's based on historical fact. If I flip this coin enough, we saw it with Excel, with the coin flipper, and the red black cards thing there. I got heads, I got tails first, I got heads that time. That doesn't mean squat. I mean, I could definitely get clumps. I got heads again. So, 50-50. That isn't the question I want to answer today. Today's question is this. If I spin this penny and allow it to fall under its own time, so don't interrupt it as it's spinning by catching it and slapping it on my hand, if I let it fall, the question I want to answer today is, what is the probability, what's the probability that a penny lands heads up after, you shouldn't have.
No.
You shouldn't have. Not with me anyway. Don, I think, does it in 243 sometimes, but you wouldn't have done it with me because I saved it here. Heads up after spinning. And I'm going to put 2 rests on here because you're going to let that bad boy fall on its own. Mine's heads right there. That doesn't mean squat. That's one data point. So what we're going to have to do, friends? Everybody get a penny. Everybody get a penny. Hand this around. Now here's the deal. I've thought about this experiment quite a bit as I've gone through the 10 years or 15, whatever, 10 years I've been here, 10 years before this. You don't want to spin these on your desk. Not in this room anyway. And why is that?
Fall off.
Well, they're slanted. So there's going to be an unfortunate consequence of spinning pennies on this desk that I don't want to measure for. Not to mention there's a little tiny groove at the top. And if the penny gets into that groove, it can goof up. What I want to do is I want the only force on this penny to be its spin. I don't want gravity. Gravity's going to be pulling on it straight down, but I don't want any kind of a vector force pulling it also side to side, which that would do. So what you're probably going to have to do is wander around MODOK until you find a nice flat area to spin them. If anybody needs a spinning tutorial, come on up to the front. We can teach you how to spin a penny. Everyone, I forgot. That's not what everybody has to do. I mean, every turn. Let's pay. We can tutorial. So, get a penny, go out, find a nice flat spot, spin it 10 times. Spin it 10 times, and keep track of heads and tails. All right? You might do it right here. Just if you're doing it on the floor, make sure none of the tiles are popped up. Make sure there's no crud on the floor that can hit the penny. You don't want the penny hitting things and interrupting. You want the penny to come to a complete rest on its own after 10 spins. Does that make sense?
Would how hard you end up spinning it matter?
It doesn't matter. That's a great question, actually, Cassie. As long as it gets spinning, if you will, the physics kicks in. So what you don't want to do is kind of spin it like that, because it doesn't get a chance to get the full speed. You want to just spin it hard enough so that it gets going like that, and now the physics is in, and now it'll slowly, as friction builds, it'll slowly drop to its side. Kelly.
I'm laughing because I don't think I know how to do that.
Well, you're all doing that now, like I told you not
You
to.
can get elected.
So go on. Go.
Everyone laughs when you talk about
We can
picking
do a
lessons,
lesson
but
up
I
here, it's
think
okay. I'm gonna turn the camera off, we'll get some data. If you need to wander out in the hallway to spin it, that's totally fine. The key is keep track of how many heads and tails. We'll come back and we'll collect our data together.
Yeah.